Hey, biologists, welcome back. We are going to be talking about Chapter 3, pH and buffers, in today's mini lecture. First up are the must-knows. We are going to talk about the pH scale, talk about how to read and interpret this, as well as talk about buffers. We'll define that and their relation to biological systems. We'll give a few examples there as well. So you may recall from our properties of water how we have the slight positive and slight negative. So we're going to start to see some of those. Notice the dashed lines. That's that hydrogen bonding going on. But we look at water, we can identify it as what's called a self-ionizing property about it, in that it will actually interact with itself. So it is both an acid and a base at the same time, which is why in a moment when we take a look at our pH scale, water is like perfectly in the center. It's not an acid, it's not a base, but technically speaking, it's actually a little bit of an acid and a little bit of a base. Just to refresh our memory about the Bronsted-Lowry definitions, one of our three definitions of acids and bases, and the one that we will be referencing for biology class, we're going to focus specifically on this. We're going to talk about gaining and losing of protons or hydrogen ions, the H plus. So when we look at this, we can see the first example gains a proton. We have that H plus, that proton, if you will, is going to be added to a water molecule to create an H3O plus or hydronium ion. And then oppositely, if one end is gaining a proton, the other side will be to lose the proton or subtraction of that hydrogen molecule, that H plus. So then we create a hydroxide, the OH. That happens to be one of our polyatomic ions. Again, you may recall from chemistry class. So we can see the visual up above. Now we have our H3O plus. It has a slight positive charge, and then we have the hydroxide ion with the negative charge. Again, self-ionizing. It will react with itself. So it's a unique property about water. Now, there's not many things that will do that. And as we kind of identified in the last slide, by definition, what our Bronsted-Lowry or our definition of acid is going to be is that we are increasing the concentration of hydrogens. So for anything to be an acid, if we're looking at the title or names or formulas of things, we should have that hydrogen in front, and it should have the word acid in there somewhere in the name. Whereas oppositely, bases, what they are going to be doing is reducing the amount of H plus concentration, that proton. And so, for instance, sodium hydroxide, NaOH, would be a great example. So a lot of things biologically, they fall generally somewhere in the neutral range, about 6 to 8. Our pH scale in reference goes from 0 to 14, although there are some extreme cases in which can go beyond that. There are actually some things that are so acidic they'll go into negative values, or some things that are so basic they will go above 14, into 15 and 16, and so on. But generally speaking, biologically, we're going to focus about the neutral range. We really don't want things to be acidic too much because those will burn and dissolve our cells and interact negatively, or opposite, we don't want things too basic because those can have a similar effect, which could damage our cells. So we want to stay within a very particular range. And we'll talk about that in a moment, why we want those ranges. Here's a few examples as we look at our pH scale. So we go from 0 here at the top, represented all the way down to 14. Relatively speaking, we have things like a battery acid. Again, it has acid in the name. And we have things like lemon juice, which has citric acid in it. We have vinegar, which is acetic acid. And these names are not the commonplace names that you and I would say. We would say lemon juice and vinegar. Like we would say those things. But in actual chemical terms, the citric acid and acetic acid, those would be the chemical names for those. Moving all the way up to black coffee, I have just about every morning here is slightly acidic, not super acidic. But as we progress towards 7, now we get to water, we get to blood, we get to tears, some of the more biological things. Saliva's in there. And then we progress into more of the base region, where we start to have more of our hydroxide, our OH ions, milk of magnesia. We have ammonia. So if you recall, if you had in the past that smell of ammonia, don't stick your nose in it. You want to open it and waft it towards your nose. Always good to practice your wafting skills. But it's very basic. We get to bleach, we get to oven cleaner for sure. And if you've ever used or looked at the oven cleaner bottle, it has a big warning label. Please do not ingest, call poison control, etc., because it is so basic, it will definitely negatively impact your living cells. It's not good to have that. So this is a relative speaking kind of in general good reference for things that are on the pH scale. So we have cleaners are generally towards the base end, and we have more citricy things and acidic things that have that soury taste, like lemons and things, that are going to be more towards the acidic. The good visuals I love on the left-hand side of this image, the acidic solution, neutral solution, and basic solution. Again, take a look at the acidic solution. Look at all of those H pluses represented by the red color there, and the little amount of OH. There's not a lot, but there's not a lot of the OH, the hydroxides, but there's a ton of those H plus. Again, we're increasing the concentration of that H plus. Whereas if we go to the basic side, it's the flipped, it's the opposite. Look at all the OH minuses, so all those hydroxide ions. There's lots of those. We're increasing in the hydroxide ions when we get to the basic side. So buffers, since we're talking about acids and bases, that is what is by definition meaning a resistance to change. So a buffer would be if something is trying to push things to be more acidic or more basic, this buffer comes in and says, no, you don't. You're not going to change the pH no matter what. Well, okay, maybe not no matter what, because if, given enough force, things will break there. But buffers will resist change. And we need this to be very specific pHs for biological reasons. For instance, blood. Blood must be between a certain pH range. 7.4 is approximately a good, like that should be on average what your blood should be. If it gets above or below certain thresholds, so like below 7 or above 7.8, you could lead to severely detrimental things. We'll talk about why a little bit later when we get to proteins, but basically, things stop functioning if they're not within those parameters. That kind of ties into this whole concept of homeostasis, why we need to maintain certain conditions internally so that we don't cause internal harm. And buffers are a good way that we can stop one condition being the pH of our internal systems. So another thing about acids and how they can affect different biological systems would be ocean acidification. So, for instance, as the infographic on the left hand shows, if we have not just jetliner, but just carbon dioxide in general, actually has the ability to dissolve within water. And as it dissolves, you can see there is a slew of arrows moving in a downward progression. It actually creates what's called carbonic acid. Again, acid, it's acidifying it or creating a lower and lower pH, driving that H plus concentration higher and higher. And so that acidic things, if you think in reference to us, if you ever gotten like lemon juice in a cut, don't do that, it really hurts. But if you ever did, it burns and it starts to react violently with living tissue. So if we start to cause this within our oceans, it will do a similar thing to surrounding environments. Coral reefs are one of those things that is they're very touchy, they're very specific to environments, and they can be manipulated into either into being damaged very easily. So they're very finicky. You gotta be very careful with them, and so it's very easy for them to become damaged. And so this is a great example to see kind of in real time ocean acidification in process. So there's a 3-panel image moving on the left, which is a fairly healthy ecosystem, and then all the way over after ocean acidification has then hit and then caused all sorts of detrimental damage to this aquatic ecosystem, it is actually destroying life in the area. Now, of course, this is an extreme example, but this is a real thing that is happening. It's actually causing what's called the bleaching of our coral reefs. And so this is something we need to be aware of is the acidification of our environments, oceans being one of them. Acid rain or the lake effect from rain causing acidification as well, not just in oceans, but also within our rain can cause detrimental damage to ecosystems as well. Look at these trees over here. The middle ones specifically, they don't look very healthy. Again, because that rainwater that's being absorbed and moving into or evaporated into the cloud system and then being precipitated on the local environment, it's slightly acidic, which, as I mentioned, is going to cause detrimental damage to living tissue, thus damaging the local wildlife. So here's a few examples, talk about acids and bases and pHs and buffers. Here is a brief overview, if you would like, of all of our properties of water and how they relate to life in biological examples. Thank you all for watching. Let me know if you have any questions.